Hello all, welcome to this course on time series modeling and forecasting using R. Now again, if you vaguely remember where we stopped in the last lecture, and rather the focus area of this entire week would be on modeling some volatile markets, or how do you capture or how do you put forward some models to capture the changing variance aspect of a time series, or how do you model volatility. Okay. Now again, in the same spirit, in the last lecture, if you remember, we discussed kinds of variances, where we talked about conditional variance, unconditional variance, and then we talked about different kinds of volatility. So now, before we start with anything new in today's session, so we'll try to elaborate a bit more on the very first kind of volatility that we discussed, which is called as HV, or historical volatility. So we'll not go into detail in each and every kinds of volatility. So again, if you remember, we talked about 4 such kinds, right? So historical, realized, and then right, and then you had 2 more kind of volatility which are seen in the markets, right? Implied volatility, right, and then volatility clustering. So these are the 4 kinds of volatility we discussed. But the very first kind of volatility is called a historical volatility. We will try to elaborate on that a bit more. So historical volatility, or in short HV, measures the variability of an asset's returns over a specific period in the past, right. Rather, historical volatility quantifies the dispersion of an asset's past returns and is typically expressed as the annualized standard deviation of the daily returns. So as discussed even in the last session, how do you find out historical volatility, or what do you mean by HV is nothing but HV is a very pure measure of the standard deviation of past asset returns. Okay. So again, historical volatility quantifies the dispersion of an asset's past returns and is typically expressed as the annualized standard deviation of the daily returns. So it reflects the uncertainty or risk associated with the asset's price movements during a given historical period. Okay. So let us say if you are sitting today and then you want to focus, or you want to find out or get an idea about how the variance has been behaving or variance has been changing in the recent past. So for that, you can actually go ahead and then try to find out the value of the HV for that. Okay. So now what exactly is the interpretation of HV, or interpretation of historical volatility? So the first is high HV, right. So high historical volatility indicates large price swings and a higher level of risk. Okay. So there would be large price swings and there would also be higher levels of risk, and this is a very typical for speculative stocks or cryptocurrencies. For anybody who wants to speculate as to what would happen in the future in a particular stock or a cryptocurrency, then you have to also encounter or focus on such large price swings or the higher level of risk which is associated. At the same time, what do you mean by low HV? So low HV suggests smaller price fluctuations and a lower risk, often seen in stable assets, for example like government bonds, etc. So whenever if you have any stable asset like a government bond or something like that, then people don't assume, let us say, really highly volatile structures, then you can actually assume some lower volatility. So suggest some smaller price fluctuations and lower risk. Okay. And lastly, changes in HV. So changes in the historical volatility. So sudden spikes or drops can signal some market uncertainty, upcoming events, or shifts in the investor sentiment. So interpretation of HV is one can actually encounter high HV, low HV, or how can you sort of capture some changes in HV. So changes in HV could be captured using sudden spikes or drops in the signal, which can due to some market uncertainty, some upcoming news, upcoming events, or simply some shifts in the investor sentiment. Okay. Now thirdly, we will talk about what exactly are the limitations of historical volatility. So firstly, this HV is a backward looking measure. Now what do you mean by backward looking? So backward looking means that HV only reflects the past price behavior and does not account for any future events which may impact the volatility, isn't it? So since you are only focusing on capturing the standard deviation of the past returns or the past data, so HV is always a backward looking measure. So it won't have a tendency of, let's say, forecasting in the future. Second is HV is highly sensitive to time period. So the length of the historical window chosen, let's say 20 days or 100 days, can significantly impact the calculated HV. So are you averaging over the last 20 days and then finding the variance of that, or are you averaging over the last 100 days and finding the variance of that, right? So these two would be, or rather can be, highly distinct. Third is outliers and noise. So extreme price movements can skew the HV making it less representative of a typical asset behavior. Okay, so extreme price movements can skew the historical volatility, making it less representative of the typical asset behavior. And lastly, ignore some structural changes. So, HV assumes that past market conditions are similar to the current or future conditions, which obviously may not hold during regime changes or crises, etc. So, again this is a clear limitation of the HV, because HV sort of ignores any structural changes. So, let us say if you have some regime change or there is a sudden crisis, for example COVID, right. So, all these ideas would kind of impact the HV calculation very heavily, because HV only focuses on the past data. So, if a sudden event comes in or a sudden regime change comes in, right, or a sudden crisis comes in, then HV does not encounter or kind of focus on any of these ideas. So, a couple of limitations that we have outlined about the HV, and hence why not one moves to a slightly different or rather improved measure of volatility. Okay. So, rather than simply finding out the historical volatility using HV, right, why not one tries to put forward a model to capture the underlying changing variance, and this is exactly the essence of, let us say, today's lecture or maybe the next one or the one after that. Okay. Okay. So, lastly a few practical examples where one can actually see some volatility happening. So, first one is risk management in finance. So, a financial institution might model the volatility of a stock price to estimate the potential risk exposure in its trading portfolio and adjust accordingly. So, adjust the capital reserves accordingly. Okay. Second could be in portfolio optimization. So, portfolio manager might use historical volatility estimates to balance a portfolio of stocks, bonds, commodities, ensuring that the overall portfolio volatility is within some acceptable limits. Third is, let us say, forecasting future asset prices. So, a hedge fund might use volatility models to predict the likelihood of price jumps in the underlying asset, such as, let us say, during earnings reports or macroeconomic announcements, etc. And lastly, market sentiment and behavioral finance. So, investors use the VIX, which is nothing but the volatility index, to adjust their portfolios based on some perceived market risk. For instance, or for example, if the VIX is rising, they may reduce exposure to riskier assets like stocks and increase holdings in safe haven assets like bonds and golds. So, all these adjustments could be easily made if one put forward and try to analyze and study the underlying volatility in the market. Okay. Okay. So, I think now we are in a position to sort of move ahead from the HV, because we have seen some limitations of HV, and now the idea is to put forward some actual models, right. And these are the exact two models we even discussed in last lectures. First one is ARCH, second one is GARCH or generalized ARCH. Okay. So, again ARCH stands for autoregressive conditional heteroscedasticity, and then GARCH stands for generalized ARCH basically. And these two are very famous models, and of course, their extension that we will study later on, to capture the volatility in the market. Okay. So, a small primer about volatility models. So, let us say YT be the log return of an asset at time t. So, YT is the actual time series we have, and what does YT contain? So, YT measures nothing but the log return of the asset at time t. So, one can say that the series YT is either serially uncorrelated, or one can actually assume some minor lower order correlation. So, one can actually assume that YT is entirely serially uncorrelated, or you actually have some minor lower order correlations, but it is assumed to be a dependent series. So, YT is assumed to be a dependent series. Now, let capital Ft minus 1 be the information set up to time t minus 1. Then in that case, the conditional mean and variance of YT given Ft minus 1 is given by expected value of YT given Ft minus 1, which is nothing but mu t, and variance of YT given Ft minus 1, which is nothing but sigma t square. Okay. So, expected, the conditional mean, which is expectation of YT given Ft minus 1, is assumed to be mu t, and the conditional variance, which is variance of YT given Ft minus 1, is assumed to be sigma t square. Okay. And again, just to repeat, what exactly is this capital Ft minus 1? So, this capital Ft minus 1 is nothing but the information set, which is kind of exactly similar to the omega we saw in the last lecture. Okay. So, capital Ft minus 1 is nothing but the information set up to the time point t minus 1, and using that information set, I can immediately write down the conditional means and the conditional variance of the log return, which is YT. Make sense? Okay. Now, what we will do, or rather what we will assume, is that let YT follow a simple ARMA PQ model. Okay, so let yt follow a simple ARMA PQ model, and we can write down in a slightly alternative manner like this. So, yt is assumed to be exactly equal to mu t plus et. Okay, so what exactly is et? Et is nothing but the random error. So, I will write down error here. And what is mu t? So, mu t is nothing but the conditional mean we saw in the last slide. Okay. So, mu t is nothing but expected value of yt given ft minus 1. So, this is mu t. Okay. So, if you add this conditional mean to a small random error, we actually get hold of an ARMA model, and then rather an ARMA PQ model. Okay. So, we will start with this guy. So, this is nothing but expected value of yt given ft minus 1, which is nothing but the conditional mean, which is exactly equal to mu t. And now, this mu t can be expressed as an ARMA PQ model. So, what we are assuming is that mu t equals phi naught plus summation I going from 1 to p phi I into yt minus I plus a different summation where j goes from 1 to q theta j into et minus j. So, you have this underlying ARMA structure here with orders of PQ. Okay. So, the AR order is P, the MA order is Q, all the phi i's and all the theta j's are the coefficients. And secondly, on top of that, we can actually assume that you have this conditional variance also. So, variance of yt given ft minus 1 happens to be sigma t square. Thus, the conditional mean of yt given ft minus 1 evolves through the interaction of past observations and shocks. So, in general, we are trying to put forward a model on this conditional mean, and we are sort of assuming that the conditional mean follows a ARMA process. Okay. Similarly, rather than focusing only on the conditional mean, can't we also analyze and study the conditional variance? The answer is yes, right. So, similarly, the conditional variances may also evolve through the magnitude of its past shocks and some of the past variability. So, the sigma t square component could also be analyzed in a similar manner. Okay. So, the whole idea boils down to, can we put forward a suitable model to capture the tendencies or the behavior of the sigma t square component. Thus, the conditional heteroscedastic models are concerned with the evolution of sigma t square component. So, how does the sigma t square component behave? How does the sigma t square component evolve over time, right? So, we require some conditional heteroscedastic models to answer such questions, right. So, the conditional heteroscedastic models are concerned with the evolution of sigma t square, the manner under which sigma t square evolves over time. And by the way, this is the exact definition of volatility. So, volatility is nothing but the under root, or rather the positive under root of sigma t square, which is nothing but similar to a standard deviation. Okay. So, sigma t, which is nothing but the positive square root of sigma t square, is called the volatility. Okay. And lastly, volatility measures the size of the errors made in modeling returns and other financial variables. So, we have been discussing the impact and the definition of volatility even from the last lecture, and this is just a small repetition here. Okay. But again, this might be a small motivation to all of you as to why should we actually put forward some conditional kind of changing variance models, right? Because again, sigma t square evolves over time. So, wouldn't it be a good idea to put forward a model on its behavior? The answer is yes. So, rather than only focusing on conditional means that we have been doing so far, why not also focus on the changing variance aspect of the time series? Okay. Now, the next thing is the conditional heteroscedastic models can be classified into two general categories, right. So, this is a small classification when it comes to capturing the conditional heteroscedastic models. So, conditional heteroscedastic models can be classified into two general categories. First one is use a stochastic equation to describe sigma t square. So, one can put forward a simple stochastic equation to describe the behavior of sigma t square. For example, let us say stochastic volatility models, or rather SV models. Okay. So, what one can do is one can create, or one can have an equation where sigma t square is one of the components and some stochastic equation on the other side. Then the second kind of a method is use an exact function to govern the evolution of sigma t square, and this would be entirely the focus of this week here. So, the first kind of a model is ARCH, which is autoregressive conditional heteroscedastic model, or ARCH, or the generalized autoregressive conditional heteroscedastic model, or GARCH. Okay. So, again, just to summarize, the first kind of a technique that one can follow is to create a simple stochastic equation to describe sigma t square, and such equations are called as SV models. On the other hand, one can actually use an exact function to govern the evolution of sigma t square. And in the same spirit, we can study the arch models or Garch models, etc. Okay, now the actual model building process, right. So, how does one go ahead and then try to build the either the arch model or the Garch model or some of the extensions there. Okay. So, building a volatility model for a time series consists of 4 important steps, right. So, the first step is obviously specify a mean equation by testing for some serial dependence in the data, and if necessary building a time series model, let us say ARIMA for the time series to remove any linear dependence. So, obviously before one can focus or counter the variance aspect, one has to tackle the mean aspect first, isn't it. So, the first point is specify a mean equation, and one can actually put forward a mean model, let us say ARMA, ARIMA, SARIMA, whatever. So, all these are examples of capturing the mean underlying the time series. Okay. The second point is use the residuals of this mean equation that we have found out in the first step to test for the arch effects. So, then we have to actually test out whether the underlying series or the underlying residuals of the mean equation contain some arch effects or not. Now, again what do you mean by that? So, we are more concerned whether the residuals show some changing variance tendencies or not. So, arch effects means that there has to be some changing variance or there has to be some heteroscedastic nature in the underlying residuals. Okay. So, one can actually go ahead and then test that. So, try to put forward a mean equation, gather the residuals of that model. So, let us say you put forward an ARMA model or ARIMA model, right. So, once you fit the ARMA model, you will obviously get the residuals. Use the residuals of the mean equation to test for the arch effects. So, we want to make sure that whether the residuals of the mean equation contain some changing variance aspects or not. And then you have a bunch of arch tests for that. So, we will discuss a couple probably soon on the next lecture, but we have some formal tests of kind of showing that. Okay. And now, once you show that you do have some arch effects, then specify volatility model if arch effects are statistically significant and perform a joint estimation of the mean and volatility equations. So, once you are through with the second point, then once you confirm that the residuals do show some arch effects, then you can actually put forward a model on that and then try to jointly estimate the mean and variance using couple of equations. And lastly, as always, check that the fitted model carefully performs well and refine it if necessary. So, this is the diagnostic checking aspect. So, of course, the diagnostic checking is not one can't ignore that here. So, once you put forward any model, be it ARMA, ARCH, whatever, after the modeling exercise has been done, one has to ensure that the assumptions are being met or not. Okay. So, for that this diagnostic checking step is kind of very important. So, hopefully this is clear that first try to model the mean, gather the residuals from the mean, test for the arch effect in the residuals. If yes, then put forward a stochastic model on the variance or put forward a volatility model if the arch effects are there, and once you model using either arch or Garch or one of its extensions, then perform the final diagnostic checks. Okay, so now we will give a very brief introduction to the arch model. So, arch is called as autoregressive conditional heteroscedasticity models, are a class of statistical models which are widely used to model time series data with varying volatility over time. So, if you have to capture changing variance, then one can actually put forward an arch model. Okay. Then these models are particularly useful in financial markets where volatility is time varying and often exhibits clustering. Now, again we have mentioned number of times as to what you mean by clustering, that is large changes tend to be followed by large changes and small changes tend to be followed by small changes. So, the changing variance also occurs in clusters. By the way, this entire idea about arch model was introduced by Robert Engel in 1982 to model the time varying volatility in financial time series. The primary feature of arch models is that the variance of the error term, or rather the variance of the residuals, is modeled as a function of past error terms, allowing for some heteroscedasticity, which is nothing but non-constant variance. Okay. So, in a way, if you allow the errors, or rather let us say ET, to kind of follow or kind of depend on its own lags, let us say ET minus 1, ET minus 2, right. So, this is exactly or rather one way of slightly bringing the volatility models into play, and this is the whole idea about arch models. Okay, so initially we will study very briefly as to what the arch model structure is all about. So, in arch model the shocks, which is ET, are serially uncorrelated but dependent. So, we require some assumptions here that the ETs are serially uncorrelated but dependent. Now, this dependence of ET can be described by a simple quadratic function of its own lagged values, and exactly how. So, in general, if you talk about arch M model, so arch M model means the order is M. So, the arch M model is a two-fold kind of a model, or you have multiple levels there. So, the first level is ET equals sigma t into epsilon t. Now, again remember what is ET? ET are the shocks, or ET are the random errors, right? And we are basically telling that ET has to also depend on the variance. So, ET is nothing but sigma t into some other IID random variable. So, these are completely random errors. So, epsilon t's are entirely random errors, ETs are the shocks of the time series. So, this is the first level of the equation, ET equals sigma t into epsilon t, and then we also show how the sigma t square, or rather how the variance changes. Okay. And then again, if you remember, probably you can pause the video here and try to answer my question, that this kind of a model structure is similar to what model structure? So, again my question to all of you is that if you observe this equation for a second, so which underlying time series model can be described using this equation? And then again the answer is AR, isn't it? So, this is nothing but the AR model. Can you see that? So, you have the dependent variable or the actual series which is being modeled on the left hand side. The alphas are the coefficients. So, alpha naught, alpha 1, alpha 2 up to alpha m, and all these are the residuals, right. So, et minus 1 square, et minus 2 square up to et minus m square, and hence the order of this arch model is m, because how many terms in the past you have? You have m terms. Okay. Again, just to reiterate the level, so the first level is concerned with ET. So, we are kind of assuming, or rather we are stating that the error is behaved as if it is equal to sigma t into some other random error, which is epsilon t. And second level is we are throwing in, or we are trying to model the variance using an AR structure, or a autoregressive structure in this manner. So, sigma t square is alpha 0 plus alpha 1 et minus 1 square all the way up to alpha m et minus m square. Okay. So, of course, again where epsilon t is a sequence of IID random variables with mean 0 and let us say variance is 1, alpha 0 is positive and each of the alpha i's are non-negative for every I. So, this is all about the arch M model. Okay. This is all about the arch M model, and again some properties or some assumptions we require. So, alpha I should satisfy some regularity conditions to ensure that the unconditional variance of ET is finite. So, again we do not want the unconditional variance of the errors to go to infinity. So, we require some restrictions on each of the alpha i's. Okay. Secondly, epsilon t is assumed to follow the standard normal, or rather a standardized student's t distribution, or a generalized error distribution, etc. So, the final random error that you see in the equation, which is epsilon t, one can, as per the regular assumptions, one can assume a normal distribution, or one can put forward a slightly different distribution also, let us say student's t or GED, etc. Okay. And lastly, under the arch framework, large shocks tend to be followed by another large shock. So, you can see some leverage effect even here. Okay. So, now again if you boil down to the arch 1 model. So, again if you remember the arch M equation, one can immediately write down the arch 1 model, right, because M is 1. So, basically M equals 1 here, and then immediately we get this 2 level model again. So, Et is nothing but sigma t epsilon t, where my sigma t square is nothing but alpha 0 plus alpha 1 into Et minus 1 square, and then you stop here. Okay. Because since you are fixing the order to be 1, you will not go beyond the first lag. And of course, here these are some other assumptions or other conclusions or other corollaries. So, expected value of Et is expectation of Et given Ft minus 1. So, this is using the Tower property. So, I am not sure how many of you are aware of Tower property. So, if you want to find out the unconditional mean of something where you already have access to the conditional structure, you can actually write it down this way. So, you can have two expectations. So, expectation of the conditional mean. Okay. This is nothing but equal to expectation of sigma t into expectation of epsilon t, which happens to be 0. So, in a way one can actually prove all these properties about the arch 1 model as well. So, if you talk about the unconditional mean, so expectation of Et, that has to be exactly equal to 0. Okay. And now the second thing is variance function. So, further variance of Et is nothing but expected value of Et square and again I can write down in a tower property kind of a statement here. So, expected value of the conditional variance, or rather E of et square given ft minus 1, which is expectation of this guy, which is nothing but alpha naught plus alpha 1 expectation of et minus 1 square. But again, just for a second, if you observe here, so expectation of et minus square is nothing but can be written down as variance. And why is that? Because we are assuming et to be a stationary process. So, each of these expectations, expectation of et square, expectation of et minus 1 square, or for that matter at any lag, have to be exactly equal. So, eventually we get this equation. So, variance of et equals alpha naught plus alpha 1 into variance of et minus 1, and one can actually combine a few entities here and then conclude that the unconditional variance is nothing but alpha 0 divided by 1 minus alpha 1. So, this is just an attempt to kind of prove two things. So, unconditional mean under the arch 1 setting or arch 1 model, and then the unconditional variance. Okay. So, expectation of et and then the variance of et. And lastly, we will discuss very briefly some limitations of the arch model. So, the model depends on the square of the previous shocks, and almost all of you must have seen this tendency, right, in the earlier slides. So, the model actually depends on the square of the previous shocks. Hence, the positive and negative shocks have the same effects on volatility. In practice, the price of a financial asset responds differently to a positive or a negative shock. Secondly, often over predicts the volatility as it responds slowly to large isolated shocks to the return series. So, this is again one limitation of the arch model, that the arch model often over predicts the volatility as it has a tendency of responding slowly to large isolated shocks to the return series. And thirdly, parameter explosion. So, what do you mean by that? So, if the number of parameters grow with the order of q, right. So, the number of parameters grows with the order of q, right, because let us say if you are putting forward a ARMA PQ model initially to capture the mean, right. So, the number of parameters grow with the order of q. So, if q is really large, right, or for large q, the model becomes complex and computationally expensive. So, again these are some limitations as to why people move from an arch model to a generalized arch model. Okay. So, obviously in the next lecture and the next lecture after that, we will try to study the G arch model and maybe some of the very famous extensions of arch and gauge, which are again very applied. But again, one final point before you close this session is that almost all the examples where one can actually put forward an arch model or a gauge model could be seen abundantly in financial literature. So, if you want to capture the financial volatility, so in the underlying markets, right, let us say cryptocurrencies, options or stocks, right. So, arch and gauge is just to capture the volatility, and then abundant examples are found in the finance kind of a context. Okay. Thank you.